Hello, welcome back to this YouTube channel. So today we're going to be discussing coordination compounds, reading of NCRT. So obviously I'm not going to read the entire thing, but I'm going to read each paragraph and then explain or tell things that I think that are very important. This video will be very small, but I will read each paragraph and tell my thoughts on each of them. So yeah. So obviously the first thing that I learned from this paragraph was chlorophyll, hemoglobin, and vitamin B12 are compounds of iron. I mean magnesium, iron, and cobalt that we all know, right? And analytical reagents, industrial catalysts, and all that is used in for this thing. And Werner's theory just stated that there is primary and secondary valence for a metal ion, and he conducted experiments on four cobalt compounds, and we have to mug up all these colors. So COCl3.6NH3 is yellow, COCl3.5NH3 is purple, COCl3.4NH3 is green, and COCl3.4NH3 is violet. Like basically, I have no idea what's the difference between these two, but I guess we'll have to mug it up like that. Maybe they have difference in the coordination, what do you say, the structure, or like the hybridization type. I don't know. Yeah, so one more thing he told is that actually he made a like he found that some of the chloride ions can be precipitated as AgCl on adding excess silver nitrate solution in cold, but some have remained in solution. So in these two, I have no idea why the color is different, but I don't know. Like, I have no idea why the color is different. So yeah, that's my one doubt. Yeah, so he's just, yeah, it's like something to ponder upon. That was one of Werner's like disadvantages, I guess. So I'll be summarizing Werner's proposals. First one is that it shows two types of linkages, primary and secondary. Second one is that primary is ionizable and are satisfied by negative ions. Okay, the secondary is non-ionizable and they are satisfied by neutral molecules or negative ions. Okay, then ions groups bounded by the secondary linkages to the metal have characteristic spatial arrangements corresponding to different coordination number. So next they talked about difference between double salt and a complex, and they give a bunch of double salts. Carnallite, KCl.MgCl2.6H2O, more salt, FeSO4. Basically, this is the formula of carnallite, right? Then potash alum formula they gave. So obviously this can be asked as J means PYQ. So yeah, I've written all the ions over here, and they told it will get dissociated to simple ions completely when it's dissolved in water. But however, these two do not get dissolved. And I'm gonna be skipping all of this shit because I don't think it's useful. So yeah, in this paragraph, they're just talking about the definition of coordination compounds. I am presuming that we all know all of this, like coordination entity, central atom, ligands. But ligands, they have said something quite a bit about macromolecules. Macromolecules such as proteins can also act as ligands. Then they've given ethane 1,2 diamine, that too everybody knows. Oxalate being a ligand, that everybody knows. And they gave ethylene diamine tetraacetate. Ethylene diamine tetraacetate, EDTA, is an important hexadentate ligand. It can bind through two nitrogen and four oxygen atoms. Obviously, we don't need to remember this structure, but it's fairly simple. It goes just by the definition. Yeah, so the next one talks about nitrite 2, nitro 2, all these what do you say, linkageism type. They just talk about the ligands that can link from both to multiple atoms in one, and obviously there'll be an important point pertaining to SCN or these kind of linkage isomers soon. This is all useless stuff. If you want, you can go through it by pausing the video. They only told something decent about homoleptic and heteroleptic that we tend to miss, which is homoleptic is one kind of donor group, heteroleptic is more than one, and that just comes by the name, right? And yes, I'll be skipping nomenclature for now because it is very, very easy and we all have probably learnt it. Then we have isomerism in coordination compounds, as you guys can see. So yeah, I mean, isomerism is kind of obvious. Stereoisomerism and structural isomerism, obviously, same thing is there in what do you say, organic. And these four, though, you all know, you need to find the specific stuff, right? And I'm going to be skipping GI because everybody knows how to get GI. Everybody knows what is FACMAR. Everybody knows all of this. Everybody knows what is optical. So yeah, I'll be skipping that. But one thing that is brought to light over here is linkage isomerism. It's also covered in my NCRT video. So as you guys can see that this specific compound, the CONH35NO2Cl2, if it's when it's obtained in the red form, actually, it's bound by oxygen, and when it's obtained in yellow form, it's bound by nitrogen. That's all. Like, basically, he's trying to tell that this is also an existing isomerism, and that I feel like it's a very important point, except for the, especially for what do you see, the colors. Coordination isomerism, to everybody knows. I mean, it's common sense, right? Ionization isomerism is also common sense. There's nothing that's special in this. Solvate isomerism also, I think it has nothing special, but I'll let you know. So yeah, actually, this paragraph ended up turning some into something important that I did not know. So solvent isomerism differ by whether or not a solvent molecule is directly bonded to the metal ion or merely present as a free solvent molecules in the crystal lattice. So it has to be present as free solvent molecule, a crystal lattice. Then only it can, come out and come inside the coordination sphere. So an example is given by CrH2O6 plus Cl3 minus, which is violet in color, but as soon as a Cl goes inside and a water escapes out, it turns gray green, which you can remember by blue is reduced when water goes out. So gray green. That's just a stupid way, but it's your wish. Also, something that I want to highlight is why Werner's theory failed. They can ask this in so many assertion reasonings. Oh my god. So basically, he questioned, like, it was questioned that why only certain elements possess this remarkable property of forming coordination compounds. It was also questioned that the why the bonds of the coordination bonds have directional properties. Why is it directed to the more electronegativity one? Like questions like that. And why coordination compounds have characteristic magnetic and optical properties. Why do they do that? So yeah, this is where, like, this one they start teaching us CFT, VBT and stuff. And VBT, I would say some of this stuff is actually common sense. I'm just going to find all of the exceptional cases and all of the weird stuff that we have missed out. So yeah, I'm going to be covering some of the basics just in case I forget. So they've given diamagnetic example as CuNH363 plus, which is everybody knows that inner orbital low spin or spin paired complex is the same thing as, like, when you say D2, that's like inner orbital, you're using the two inner orbitals of D. Then COF6, actually COF6 uses outer orbital configurations, and they're called high spin or spin free complex, that everybody knows. Tetrahedral complexes, they've given NiCl4 as an example, and square planar they've given as NiCO4 and NiCN4. That I'm pretty sure everybody is knowing that. And one thing that I found interesting is that hybrid orbitals don't actually exist. They're just mathematical manipulations of wave equations. That's all. So one more thing that I had highlighted in the NCRT video that I had published, that COC2O43 is diamagnetic, even though C2O4 is an absolutely shit ligand according to the order. But we gotta mug it up. So MnCN6, FeCN6, and COC2O43 are inner orbital complexes with D2sp3. And these three examples, though I'm pretty sure everybody knows them, but just in case you want to go through it, it's MnCl6, FeF6, and COF6. So this example states that MnBr4 is should be tetrahedral. Okay, tetrahedral. Yeah. So now we have Valence bond theory limitations, which have been asked in J-mails, and involves a number of assumptions. It involves a number of assumptions. Does not give quantitative interpretation of magnetic data. It does not explain the color exhibited by the coordination compounds. It does not give a quantitative interpretation of the thermodynamic or kinetic stabilities. Basically, it does not explain the stability, does not make exact predictions for four coordinate complexes, does not distinguish between weak and strong ligands. Okay. Now we have CFT. CFT is very important. So yeah, obviously CFT, everybody knows the reason. It's because of spherically symmetrical field. Negative charges, they only caused, like, the degeneracy of the orbitals. But it depends on what field it is, right? So if the field due to ligands, either anions or the negative ends of dipolar molecules, becomes asymmetrical due to, and the degeneracy of d orbit is lifted, it results in the splitting of the d orbitals, and that can happen because of the nature of the crystal field, which is basically nature of the ligand, right? So yeah. So in CFT of octahedral, it's splitting like that because the ligand only appears, meaning appears the metal along dx square minus y square and dz square. That's why the energy of these two orbitals are very high, and these, okay, dxy, dyz, xz are directed between the axis, and their energy will be lowered in relative to the average energy of the crystal spherical field. So degeneracy of the d orbitals have been changed due to ligand electron metal electron repulsions, and it causes T2G and EG set. So yeah, there's nothing else in this thing, basically in the octahedral splitting. We just have that it's defined as crystal field splitting, 3 by 5 2 by 5 ratio, everyone knows, right, of the from the barycenter. And yep, and apart from that, we have strength of ligands, which we have to obviously mug up, and there's nothing can do about this. As you guys can see that C2O4 is actually weak. That's why I was calling it weak back then. And this is called spectrochemical series, which is derived by absorption of light by complexes with the different ligands. Okay. So yeah, in tetrahedral system, we just have to know which orbitals they're just switched up. Like the barycenter is switched up, everything switched up. And one relation that is very common is this one: delta T is equal to 4 by 9 delta O. So yeah, this is color of coordination. This is very important. Color of coordination compounds, and yep, they have told that it's the complementary color is a color that's generated from the wavelength left over, right? So they are saying that basically color of light observed we can derive by checking strength of ligand, but color of coordination entity is the actual color which you have to mug up. I'm just going to tell them because I think I remember majority of them anyways. So violet is COCl NH35. Then if you replace that with H2O, you'll get red. CONH35H2O. You will get red. And then you'll get yellow orange if you put all as NH3. So CONH36 3 plus. Pale yellow comes only when you put, what do you say, COCN6. Then CuH24, everybody knows that it is blue in color, and TiH26, which has been asked in many PYQs, it is a violet colored compound. Here they are talking about Diddy transition in TiH26 in this bullshit paragraph, which absolutely is pointless to read. So please don't read it. So yeah, and obviously, if if there's no ligand itself, how the hell will it have a color? How is the crystal field splitting? Same thing they've done over here. TiH26Cl3 on heating renders it colorless. Now that seems kind of obvious here, but when that comes in as a question, I am dead sure we will be clueless. So please just mug it up as a reaction. So yeah, the same thing they gave for COSO4 and COSO4.5 is 2 that everybody knows, I think. This one, yeah, they have given multiple NIs, and that is something that is very important, I think. So with one NI, it is green. With one EN, it becomes pale blue. With one more EN, it becomes dark blue. And with what do you say? With all three ENs, it becomes violet, right? So you can say blue, purple, pale blue, like that. We can say. Now, color of some gemstones, which is obviously very, 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 very important. I think it's going to come this year. So, ruby is aluminum oxide containing Cr3 plus ions, which are randomly distribution potent in positions normally occupied by Al3 plus. Chromium 3 species, we can notice that it is a octahedral chromium 3 complexes incorporated in alumina lattice. The D transitions at these centers give rise to the color. Yeah, which is valid as hell. So Cr3 plus occupy octahedral sites in the mineral beryl. Okay, beryl mineral. So absorption bands seen in the ruby shift to longer wavelength, namely yellow, red, and blue, causing emerald to transmit light in the green region. So, if you somewhat remember this paragraph, you can get marks because they won't ask, like, they might ask that is this paragraph correct or wrong, and you might or might not get it wrong, right? So, just need to read through this, keep reading through this as much as possible. So we have homoleptic metal carbonyls, which they have asked number of C double bond, O bonds, and all that shit like 600 times by not least. Homoleptic carbonyls compounds contain carbonyl ligands formed by most of the transition metals. These carbonyls have simple, well-defined structures. Tetracarbonyl nickel 0, pentacarbonyl iron 0 is trigonal bipyramidal, while hexacarbonyl carbonyl chromium is octahedral. This is something that you might have to know, but it's easy. Decacarbonyl dimanganese 0 is made up of two square pyramidal MnCO5 units joined by an Mn bond. Octacarbonyl dicobalt has a CO bond between two CO groups. Okay, all these structures have to be marked up by heart. So they've given us all these structures, and these two can kind of remember. FeCO5 is trigonal bipyramidal. NiCO4 is tetrahedral. That at least I think we knew. CrCO6 is octahedral. Now MnCO10. You can remember two boxes. Like you can just remember something like a star structure like this. And CO2 CO8, as I told in the NCRT video, that it's very similar to Fe, right? And Fe, I think there is one like this, and then there's one or two. I think yeah, there's one extra like this. That's it. So as you guys can see that metal carbon, this is what synergic bonding only, right? So metal carbon bond and metal carbonyls possess both sigma and pi characteristics. MC sigma bond is formed by the donation of lone pair of electrons on the carbonyl carbon into a vacant orbital of the metal. But for pi bond, okay, they said pi and both sigma, right? So pi bond, the metal the metal donates a pair of electrons from the d orbital of the d orbital of the metal to vacant anti-bonding sigma star orbital of carbon monoxide. This can be 100% asked. This creates synergic effect which strengthens the bond. Okay, I have no idea why the hell it strengthens the bond, because it's vacant anti-bonding. Why anti-bonding karega na? So yeah, so I'm actually going to lose my shit because this importance is the most. I want to quickly summarize this bullshit paragraphs for you. So they have said that chelating ligands are majorly used in qualitative and quantitative analysis due to the formation of their colored compounds, which is including EDTA, DMG, alpha nitroso, beta naphthol, cupron. Hardness of water is estimated by Na2 EDTA titration, and because Ca and Mg form stable complexes with EDTA, and they can be separated easily because Ca and Mg form different stable compounds. So some basically gold combines with cyanide, presence of oxygen water to form this, okay, AuCN2, and it can be separated in metallic form from the solution by acidic addition of zinc. That makes it easy to extract gold. So same thing, purification of metals can happen because Ni, impure Ni can react with NiCO4, which can be decomposed to yield pure nickel. Okay, and hemoglobin is the red pigment of blood, which acts like an oxygen carrier. It's a compound of iron, and same thing you can say for B12, cyanocobalamin, which is a coordination compound of cobalt. So same, I mean, there are enzymes such as carboxypeptidase and carbonic anhydrase, which are catalysts. So you don't need to mark these up, I don't think, but you can somewhat recall it, right? PH3PRHCl, which is a Wilkinson catalyst, is obviously used for the hydrogenation. I'm pretty sure everybody knows that by now. And AgCN2 minus, AuCN2 minus can be used for electroplating, because the actually what happens is, I'm going to give a bit of an insight on this. It's an ICC thing, right? So electroplating, what happens is that if you don't use these, if you don't use these complexes, right? Ag plus and Au plus ion, they move really fast. Now, if they're moving really fast, you want to electroplate something on the cathode, for example. So in the cathode, Au will get deposited, Ag will get deposited. But if the ions are moving too fast, they won't have an even deposition on the layers. Now, these coordination compounds, their ions move really slowly. So that's why the electroplating is as smooth and as even. Okay, so yeah. Then in black and white photography, the developed film is fixed by washing the washing with hyposolution, which dissolves AgBr, okay, into AgS2O3, which is a black colored, okay. Then excess, like basically chelate therapy we're talking about over here. Chelate therapy, what does it state? It states that there are toxic stuff in plants and animals, correct? And that can be removed by using chelating ligands. Easy, as easy as that. They form stable complexes with those materials that are toxic, and boom, it's done. The work is done, all the toxic metals are gone. So same thing, EDTA is used for treatment of lead poisoning because it forms stable complex with lead. Same thing, you can also say that platinum inhibits growth of tumors by forming complexes such as cisplatin. That is it, guys. Thank you. If you enjoyed the video, please subscribe to my channel.